As we start this video, I want to remind you of a couple things that we know. We know that work comes from a force being exerted over a distance, and we know that the relationship between work and force is that you can multiply force times displacement for a constant force, or for a variable force, work is equal to the integral of F dx. Okay? And we also know that work is equal to the negative change in potential energy from the first video. We haven't really discussed this, but this is going to start to become relevant here. So when we do work with a force that's conservative, then we are changing potential energy. If you do negative work, then you're actually increasing potential energy. If you do positive work, then if something's doing positive work, then the potential energy is decreasing. So, for example, with gravity, when something gets lifted up, then gravity, the work done by gravity is negative, and it's causing a positive change in gravitational potential energy. Okay, and so that's what that relationship represents. And so if we're saying that this direction up is positive, then if we say the direction up is positive, then the force of gravity would also then be negative. Okay, and so these things are kind of related. So you'll see that the sign of the work done and the force is the same, and so we can kind of take this and put it right here. And so the negative change in potential energy is equal to the integral of F dx. Okay? And we actually want to kind of look at this in a slightly different way. So we're going to rework this and say that, so remember that the opposite of the integral is the derivative. And so if potential energy is the integral of force, then force would be the derivative of potential energy. And so we say that force is equal to the negative derivative of potential energy with respect to position. And so these are kind of the next two pieces that we're going to add in here, and this is really the one that we want to talk about. And we can use this to think about the direction of a force as it connects to potential energy. And the things that we're about to talk about can get really confusing and really abstract. And so I'm going to be showing you basically what are potential energy graphs. And so here's one right here that I'll go ahead and move to the side. And these are basically graphs of energy. And before we really dig into this, I'm just going to let you know that when we talk about this graph, it's going to make the most sense if you kind of look at this graph in some ways as a roller coaster. Okay? So like if we are in a roller coaster and we start right here, let's change the color so we can see it. So if we're in a roller coaster, we start right here, then this cart can go up and it can get all the way back to here. If you're in a roller coaster that starts right here, the cart can go here all the way back to here, but can't get higher than this point. It won't go up to there. Okay? And so this is basically a potential energy graph. And now there's points right here and right here that we would call like potential energy wells. And these are places where something can get trapped unless it has enough energy to get out. And so this relationship here, where force is equal to the negative derivative of potential energy, that's where this becomes important. So what we can say is this: if we're sliding down this hill, we have a negative slope, right? But the force acting on us that's causing us to slide down this hill is pushing us in this positive direction. And so that's why there's a positive force here. And so if force is equal to the negative derivative of potential energy, well, that would mean the negative of the slope. So if this is a negative slope, that means we have a positive force. And as we start to come back up on the other side, we're getting pushed back this way by a force. Okay, this is a positive slope, but the force is pushing in this negative x direction. Okay, And now I know that this is abstract and we've never really looked at a graph this way before, but this is essentially what a potential energy graph is. Okay? And the reason they're useful is to talk about these wells, and that we have points that would be considered like equilibrium points, where something will have like the lowest amount of energy and it'll be kind of relatively stable. So these would be called equilibrium points right here. And if you've taken chemistry, there's a connection here to chemistry graphs, like for chemical reactions where you have a certain amount of potential energy in a bond based on the position of two molecules, and you can you have to like add energy to a bond in order to break the bond, or you have to add energy to bond them together. And you've probably looked at some potential energy graphs that look kind of like this. Okay, if not, that's okay. We're going to go ahead and think about this though in terms of total energy of a system. So this graph shows potential energy, and we can now pair this with kinetic energy to talk about where an object is free to go in this system, or in this scenario, this potential energy field, we'll call it. Okay, so let's say that we have a particle that has a mass of 0.1 kilograms. We might find out that these numbers don't make any sense. We might have to go back and tweak some of these numbers. So we have a mass of 0.1 kilograms. Let's say it has a velocity of 2 meters per second when it's at a position of x equals, let's say, 3 meters. Okay, and it's a positive 2, which means it's going this way. Okay, and so the question is, well, is this particle going to be able to escape? And so does it have enough energy to get over this hill right here? And so in order to figure that out, we need to look at the total energy. Okay, and so what types of energy does this particle have at this position? Well, it's going to have some amount of gravitational, or some amount of potential energy. We don't know how much, given that it's at this position, and we know that to be here it has to have 3 joules of potential energy, and it has some amount of kinetic energy. We calculate 1/2 times mv squared. So then the total energy of this particle would then be, or we'll call it the total mechanical energy, would be the amount of potential energy plus the amount of kinetic energy. And so we could say, okay, well, it's going to have 3 joules of energy because it's here, plus it's got 1/2 times 0.1 kilogram of mass times a velocity of 2 meters per second. Okay, which when we simplify all this, that's 4 times 0.1, or 0.4, divided by 2 is 0.2. So that is 3.2 joules of mechanical energy, which means that there's kind of like a barrier for this object right here at the 3-point-joule mark. Okay, and it's never going to be able to pass this point. Okay, it can get close to it, it can come up to that point, it can get anywhere between those points, but it's never going to exceed those points because it doesn't have enough energy. Okay, and so if we gave it like a little push, we did some work, we could increase that amount of energy to like a higher position so that it could go further up. But for now, it's trapped between these 2 points. It's kind of stuck in these 2 wells here. Okay, and then we could figure out, say, like how fast it would go right here. Well, at this point, at position 4, we could say, okay, well, if I want to know what the velocity is at position 4 right there, I could say, well, the total mechanical energy I found to be 3.2 joules. At that position, we have 1 joule of potential energy. Let me solve for the kinetic energy, and then I can solve for the velocity. Okay, so with that knowledge, I'd like you to go ahead and solve for the velocity at this position right here. How fast is it moving when it's at a position of 2 meters? Okay, so when we solve for this, we're going to say that the total energy, 3.2 joules. At that position, we have 0 joules of potential energy. And so all the rest of the energy goes into kinetic energy. If this is 0.1, then we're going to say when we solve for v, we're going to get that v is equal to the square root of, this becomes, I believe, 64 joules. So we have a velocity of 8 meters per second, and it's plus or minus. Okay, and so you can think of a couple things right here. First of all, the reason it's plus or minus is because, let's say it kind of rolls this way, starts to come back down the other way. So it's negative as it goes that way, comes back, it's positive as it goes that way. Okay, and so there's two different velocities depending which way it's going. And this is kind of the basics of a potential energy graph, and it's really simple, but it's confusing because it's just so different. It's such a different way of reading a graph, okay? And so I like to think of it as like an object that's stuck on a roller coaster going back and forth, and that kind of helps me think of it. You can see that the places where the force are the greatest are the places where it's the steepest, right? It has the biggest slope, and then the direction just has to do with which way you're getting pointed on that graph, okay? And these are the basics of a potential energy graph.